All right. So looking at example 3 here, this is the whole purpose in life of inverse trig functions, is to let you solve for an angle. So here, they're asking us, what is the angle? What does it measure? And all I know is that one side of the triangle is 9, and this other side over here is 12. All right, so remember, we're going to label our sides. That's our opposite. Across from the 90 is the hypotenuse. So this third one is the adjacent. So I need the trig function that has adjacent over hypotenuse. So ka to wa. So it's not so, it's ka. So the cosine of theta in this triangle will be 9 over 12. Now, to figure out what theta equals, I am going to take the inverse cosine of both sides. And then this is something I'm going to type in on the calculator. There is a special button for inverse cosine. You can't type cosine and then put a -1 power. The calculator gets confused. So you actually have to go find the button for it. Now, on most calculators, it is hit the shift key and then hit whatever function. So like cosine, the shift for cosine is inverse cosine. And that inverse is for this, not for 1 over. There typically is not a button at all for secant and cotangent. All right. So yeah, my calculator on my phone is a little weird. I've got a like wiggle back and forth button, and that gives me my inverse trig functions. Not even sure how well y'all can read it. So we are just going to type on most of the calculators, you hit the function and then you're going to put what's inside it, 9 divided by 12. And then we close the parentheses. Now mine, a little weird, but it types a cosine. And right now, mine does not say radians, so this result is in degrees, and that sounds reasonable. 41.4096 degrees. Now, if I switch to radians and go back, I get 0.7227 radians. Now, generally, if you are answering what is the measure of an angle, if you don't write the little degrees, we assume it's radians, but it is better communication to write radians as a unit here. To be very clear, you did not mean a tiny measure of an angle, but an angle not in degrees. But otherwise, there's no good way to produce this 41.4096 degrees. Like, it's basically the calculator has a giant lookup table for these things. So back before calculators, when I say lookup table, I mean you literally had a reference book and you would open it up and have to go find like 9/12 in there, and then it'd look up 41.4096. Maybe it would have some more decimals. And that's the kind of crap we use to get astronauts to the moon. I know, I'm shocked too. All right, in figure 9, solve the triangle for the angle theta. All right, so now we have the side opposite and the hypotenuse. So OOH is our sine. So the sine of theta is 6 over 10. So we're just going to use inverse sine. So on my calculator, I'll use my a sine of 6 divided by 10. But I'm going to flip it back into degrees. So my degrees, my theta here, is 36.869. It would round to 99. In radians, 0.6435 radians. WebWorks should tell you what it wants if it even gives you the questions this way. But this is, at the very basic level, this is what inverse trig functions do, is they let you see what that angle measure is. So when you actually have to do something and you need the angle measure, this is where you go. What you do with the angle measure is up to you. What we're really going to be looking at is crap like this. So we can actually compose trig functions and inverse trig functions together, and they're not going to look all pretty like this where it would cancel out the way we were just using it. So it'll be a little more of a headache. But we do have to remember our restrictions on the domain and range of both of the things for what we pick as the values. So like inverse sine of x is only going to work when x is between -1 and 1, because I can only put into arcsine numbers from -1 to 1, because it has a restricted domain. Likewise, when I do arcsine of sine of x, I can only do this for the angles that are between -pi and 2, -pi over 2, and pi over 2. This will only spit back answers in that locale. So it takes some practice getting used to like which way are we looking at it, and what it really comes down to is what is x, which one are we applying first. So if we're applying a trig function, the x is an angle. Let me think about what are our angle restrictions. If we're applying an inverse trig function, this x is now the output of the sine of the cosine. All right. So on these, it looks like, oh, we just cancel out and write the numbers, right? Sort of. So when our angle is in quadrant 1, yeah, what you see is what you get. All of the trig functions have quadrant 1, and quadrant 1 works nicely for us. So the sine of pi over 3 is some number, and then the inverse sine of that will bring it back to pi over 3. Two pi over 3, though, is here. So I can take the sine of 2 pi over 3. My inverse sine, though, won't spit out an answer of 2 pi over 3. Inverse sine will only spit out answers over here in quadrant 4 and 1. So 2 pi over 3 is the long side, 60-degree reference triangle. So the sine of this is the square root of 3 over 2. So now I'm asking myself, all right, where in my restrictions for arcsine am I going to get an angle that will produce a sine value of square root of 3 over 2 positive? So that's got to be in quadrant 1, and then the reference angle is going to share the denominator. So that reference angle is pi over 3. So down here, we actually get the same answer as the first one. Now, a little bit different down here. Remember, cosine is defined in a different spot. Cosine works in quadrants 1 and 2. 2 pi over 3 is in quadrant 2, so we're going to get 2 pi over 3 back out. When I look at negative pi over 3, though, that's down here. So cosine is positive in the 4th quadrant. All students take calculus. So this would be positive. So we're going to have it in quadrant 1. So instead of negative pi over 3, the result we will actually get out of D is positive pi over 3, just based on where the triangle would have to be to fall within our highlighted set of numbers. All right, now it's similar on tangent, but tangent works out nice for us. Well, we still have the same restrictions. It can only spit out numbers between negative pi over 2 and pi over 2. So pi over 8 is between negative pi and 2 and pi over 2. So our first one will absolutely be pi over 8. The second one, though, 11 pi over 9, is a little bit bigger than pi. So it's actually way out here. And the tangent of this is positive. So when I'm looking at my tangent restrictions, tangent is positive in quadrant 1. So I want the quadrant 1 reference angle that matches this mess. Which means if I can figure out the measure of that little angle there, and I extend, it'll be the same as there, which is the reference angle. So my pi over 9 is pi too big. So I need to subtract off a whole pi there. So 11 pi over 9 minus pi, multiply by the 9 over 9, so my denominators match. So this will be 2 pi over 9. All right, so some of them, what you see is what you get. Others, you have to consider, all right, is this thing positive or negative? And then which quadrant of my restrictions on the inverse function has the angle that I want, the sign that I want, like the positive or negative. Evaluating the composition of an inverse sine with a cosine. All right, so we have the cosine of a number, and then we are being asked to find the inverse sine of that number. All right, so the cosine of 13 pi over 6. 13 pi over 6 is a little bit bigger than 12 pi over 6, and 12 pi over 6 is 2 pi. So 13 pi over 6 minus 12 pi over 6 is simply pi over 6. So the cosine of pi over 6, now if you're trying to remember pi over 3 versus pi over 6, a sixth of a pizza is smaller. So this is the smaller angle, which means it is our 30 degrees, 60 up here. So the short leg is the 1/2. The long leg is the square root of 3 over 2. So the cosine of our angle here is square root of 3 over 2. So cosine of 13 pi over 6, which is equivalent to the cosine of pi over 6, is the square root of 3 over 2. So when I say what is the arc sine of the cosine of 13 pi over 6, I'm really saying what is the inverse sine of the square root of 3 over 2? Well, that's positive, so I know my angle should be in the first quadrant. Where is sine square root of 3 over 2, though? So our triangle up here with the 30 degrees, sine is not square root of 3 over 2 here, that's cosine. So we need to look at the flip triangle. This puts the square root of 3 over 2 going up, and the 1/2. So this is pi over 3. So I know a whole lot of thinking and weird work, but that is how we get the angle measure that answers this setup here. So this is how we work when the regular trig function is inside. When it's outside, we're going to play it with it a little differently. But inside, it's giving us an angle definition. Then we can look up what we want from that and go on. So the sine of negative 11 pi over 4, that is a very large negative number, which is not on my unit circle, but it is an over 4 angle. So I am expecting this to be coterminal with something on the unit circle. So negative 11 pi over 4 plus 2 pi is 8 pi over k. So I'm going to add 2 times 2 pi, which is 16 pi over 4. All right, so we get 5 pi over 4 is our actual angle that we're talking about here, which is bigger than 4 pi over 4, or pi, so that is our guy down here. Now remember our 45s, the x and the y are the same number, and the ones where everything is the same, it's all the 2's. Square root of 2 over 2. So it said the sine of negative 11 pi over 4 is the same as the sine of 5 pi over 4, and that is negative square root of 2 over 2. So this is now just asking us, well, what angle value does arc cosine give you when you put in negative square root of 2 over 2? So we got to remember, where is cosine positive and negative? So we always get quadrant 1, but this is a negative 1, so we got to go to the other guy. So all students take calculus. Cosine is positive in quadrant 4. We already have positive values, so we need to go over here. So arc cosine of negative square root of 2 over 2 is going to spit out the angle in quadrant 2. And if we look on the unit circle, all of the 45-degree reference angles are the radians with over 4. So this is 3 pi over 4. So I know it's a lot more thinking, a lot less like work, which does mean like on the writing assignment, you have to talk about it more, or when you get something like this on a test. So be on the lookout for those. All right, let's take a look at this one, and then I'll probably cut it and then start a third video. So now our inverse function is on the inside. So this is saying that the cosine of some angle theta is 4/5. This question is asking, well, what's the sine of theta? So here's how I start my setup. So this guy is some angle. So if theta equals the inverse cosine of 4/5, then I can apply the cosine to both sides. And I'm told that the cosine of theta is 4/5. Well, that then is a triangle I can set up. So our cosine is adjacent over hypotenuse. This is our theta, so 4 over 5. 25 minus 16 is 9. Square root of 9 is 3 for our third side. Because our actual expression they want us to solve is the sine of this angle that produces a cosine of 4/5. So this angle we labeled theta. So then this is really just asking, Well, what's the sine of the angle that you drew over there? Opposite over hypotenuse. So our result would be 3/5. If they don't give us a negative sign, which in these type of problems they usually don't, just assume it's in quadrant 1 and everything's positive. Otherwise, it becomes a headache. All right, stop.